Imagine a world where your most sensitive data, your conversations, your finances, even critical national security stuff were truly unhackable. What if you could know, like, instantly if anyone, anywhere was even trying to snoop?
It sounds almost like science fiction, doesn't it?
Yeah.
That challenge of data security, it's everywhere in our digital lives.
Right.
But that dream, the hack-proof communication one, it's actually closer than you might think, thanks to the incredible, sometimes weird world of quantum mechanics.
Absolutely. So today we're taking a deep dive into quantum key distribution, QKD for short.
Right.
This technology, it's pretty revolutionary. It uses quantum physics principles, the really fundamental stuff, to make sure data transfer is completely secure.
And the core idea is brilliant, really. If any hacker, anyone, even tries to look at the quantum key,
they break it.
Exactly. They instantly disturb the quantum state, so you know immediately.
It's like a digital tripwire, but one that actually smashes the lock the second it's touched, not just an alarm bell.
Precisely. And what's really exciting, I think, is that this isn't just theory anymore. Our deep dive today is focusing on India's, well, quite frankly, pioneering leaps in this area, specifically through a really groundbreaking collaboration.
Yeah, that's putting them right at the forefront globally.
It really is.
And the players involved here, it's a powerful mix. DRDO, the Defense Research and Development Organization, IIT Delhi, specifically their joint center, the DIA-CoE.
The DRDO Industry Academia Center of Excellence. A bit of a mouthful, but crucial.
It is. And DRDO's own dedicated quantum technology research center, the QTRC.
So we're not just talking lab concepts. We're going to explore tangible, real-world breakthroughs, things that are positioning India as a leader in this future-defining field.
Okay, so let's unpack that collaboration first, DRDO and IIT Delhi, because it feels like the bedrock for all this. What more can you tell us about the DIA-CoE at IIT Delhi? What's its specific mission?
Well, the DIA-CoE is really designed as a central hub for joint research, specifically focusing on QKD both over fiber and through free space.
Okay.
And also creating entangled photon sources, which are key for some protocols, plus looking into advanced multi-channel QKD systems. It's where academia and defense research really come together.
And something that jumps out from the material is the focus on indigenous components. Building it all in India. Why is that so critical beyond just, national pride?
That's a really important point. It boils down to technological sovereignty. Think about it. For critical systems, defense, finance, you can't rely on external supply chains that might be, well, compromised or just cut off.
Right, vulnerabilities.
Exactly. So building it indigenously, from the single photon sources to the detectors, it creates resilience. It ensures India has complete control over its quantum security. They're not just using the tech, they're mastering its creation.
That makes a lot of sense. Okay, let's walk through their progress then, because the timeline is pretty impressive. Starting back in February 2022. That seems like the first big public milestone.
It was. That was the first successful QKD test over a 100-kilometer stretch of commercial-grade optical fiber.
100 kilometers? Wow, where did they do this?
That was between Prayagraj and Vindhyachal in Uttar Pradesh. And the significance was huge.
Because it used existing infrastructure.
Precisely. It proved you could do long-range quantum-secure communication over the telecom networks we already have. That's massive. No need to rip everything out and start again, necessarily.
And they got decent speeds, too, right?
Yeah. Secure key rates up to 10 kilohertz. They use the BB84 protocol for that one, the sort of prepare and measure scheme.
And 10 kilohertz, just to put that in context for people?
Well, it's fast enough to secure things like, say, a high-def video call in real time, or a significant data transfer. So it showed this wasn't just a lab curiosity. It was practical, high-speed stuff.
Okay, a phenomenal first step. Then, fast forward to November 2024, things seem to accelerate. Free space experiments, campus-wide stuff.
Yes, they really started pushing the boundaries then. There were lab experiments like 50-kilometer fiber-based QKD using entanglement. Also an 8-kilometer campus-wide test using optical fibers.
But the free space work sounds particularly interesting.
It really was. They shifted protocols for that using BBM92, which is entanglement-based.
Right.
And they achieved 20 meters indoors wirelessly and then 80 meters outdoors. Also a 10-meter hybrid system mixing fiber and free space with a quantum bit error rate QBER. Around 6%.
Okay, 6% QBER? That sounds low. Is that good for free space?
It's actually very good for free space quantum links. It means the signal is highly accurate, very robust, even with, atmospheric interference and things like that. Crystal clear, basically.
And again, using their own hardware.
Yes, that indigenous push continued. heralded single-photon sources, entangled pairs, those superconducting nanowire single-photon detectors, the SNSPDs, all homegrown. And importantly, they weren't just keeping it in the lab. They were building real-world test beds designed to withstand actual weather conditions.
Okay, now this brings us to June 2025. This feels like the big one, the no strings attached quantum message.
That's the headline achievement, you could say.
First, secure wireless quantum messaging over, what was it, just over a kilometer?
1.02 kilometers, yeah. And this is where the wireless capability really shows its potential.
What kind of performance did they get there?
The key rate was about 240 bits per second, which might not sound like a lot compared to, say, Wi-Fi speeds, but for secure quantum keys generated over that distance wirelessly, it's significant. And again, a very low QBER, under 7%.
Still using that BBM92 protocol.
Yes, the entanglement-based one. The setup involved free space optics, telescopes to align the beams, time-synchronized detectors for those entangled photons, and quantum random number generators, QRNGs, for true randomness.
So, stepping back, what does this wireless breakthrough really unlock? You mentioned the quantum internet earlier.
It's huge. It means quantum security isn't tethered to fiber optic cables anymore.
Right.
Think about immediate applications, secure communication for military units on the move, secure links for satellites and space missions, robust financial networks where maybe laying new fiber is just too difficult or expensive.
Okay.
And yes, it's a absolutely critical step towards a global quantum internet. Secure information anywhere without needing a physical wire. That's the long-term vision.
So we've seen these incredible milestones, but let's put into the weeds a bit, understand the how, the science and engineering behind it. We mentioned the protocols briefly. BB84 first.
Right, that was the prepare and measure scheme used in the early fiber tests. You send single photons encoded with quantum information.
And then BBM92.
That's entanglement-based.
Yeah.
Used in the more recent free space and hybrid tests. It relies on those linked pairs of photons we talked about.
And you mentioned decoy state QKD as well. What's the advantage there?
Yes. That's likely being tested too.
Yeah.
It's a clever trick, really. You mix in decoy pulses of light with different brightness levels.
Okay. Why?
It makes it much harder for an eavesdropper to perform what's called a photon number splitting attack, basically, trying to peel off a few photons without being noticed. The decoys make that kind of attack detectable, so it adds another layer of robustness.
Got it. And none of this works without the hardware. You mentioned some key components, the photon sources.
Exactly. They need reliable sources.
Yeah.
Things like heralded single photon sources, they basically signal, here comes a photon, making sure you get one at a time.
Right.
And entangled photon sources, often using special crystals like type 2 BBO beta barium borate. These generate those crucial pairs of linked photons.
And the detectors have to be super sensitive.
Incredibly sensitive. Those SNSPDs, the superconducting nanowire single photon detectors, are state-of-the-art. But they need to be cooled way down to about 2.5 Kelvin.
Minus 270 Celsius, roughly.
Pretty much, yeah, using cryocoolers. That extreme cold lets them detect even a single photon hitting them. Plus, you need very precise timing equipment, photon counters that tag arrival times accurately.
And other systems involved, managing the data, cleaning it up.
Absolutely. You need multiplexers to handle both the quantum channel and the classical channel needed for coordination. Real-time error correction is vital, because some errors will naturally occur. And then privacy amplification, that's a cryptographic step to distill a shorter, perfectly secure key from a slightly longer, potentially slightly compromised raw key.
Yeah.
And, of course, the ability to generate those entangled states, like Bell states, with very high fidelity.
Okay, those Bell states. Can you give us a quick picture again, that spooky action thing?
Sure. Think of it like having two special coins. You flip them, separate them, send one to London, one to Tokyo.
Okay.
The instant the person in London sees theirs landed heads, they know, absolutely know, the one in Tokyo landed tails. Instantly, no matter the distance.
Because they're linked?
They're entangled. That deep quantum connection is what makes protocols like BBM92 work and why they're considered so secure against eavesdropping. It's fundamental.
Fantastic analogy. Now, these breakthroughs, they need support, right? Infrastructure, a plan. Tell us more about the hubs driving this.
Definitely. The DIA-CoE at IIT Delhi, as we said, is that central hub for collaboration. It has integrated quantum test beds, bringing government and academia together to make scalable, practical solutions.
And the DRDO's own center, the QTRC.
Right, the Quantum Technology Research Center,
Yeah.
established May 2025, located in Delhi under DRDO's Solid-State Physics Lab. It's a serious R&D facility.
What kind of capabilities does it have?
A whole range. They're equipped for quantum sensors using alkali Zaper cells, experiments needing cryogenic temperatures, developing quantum memory, building atomic clocks, working on complex entanglement systems. It's a powerhouse.
So looking forward, the goals seem incredibly ambitious. Quantum satellite communications, like China's Messias satellite.
Inspired by it, yes. That's definitely a long-term goal. Establishing dedicated quantum internet nodes, maybe first between defense and intelligence agencies.
Miniaturization, too.
Yeah.
Photonic integrated circuits.
Exactly. PICs to shrink down the components, make them cheaper, more deployable, and even thinking about quantum secure mobile devices eventually.
It all sounds amazing. But are there limitations? Challenges India still needs to overcome? QKD isn't magic, right?
That's a fair question. QKD is incredibly powerful for securing the key exchange, but it doesn't magically encrypt the data itself. You still need robust encryption algorithms using those secure keys.
Ah, okay, so it's one part of the security puzzle.
A very important part. But yes, challenges remain. Extending the range of free space links, especially through bad weather or atmospheric turbulence, is tough.
Right.
Scaling up to handle many users simultaneously, and as you mentioned, reducing the size, weight, power consumption, and cost the swapsy of the hardware for widespread use.
And that's where national programs come in.
Precisely. India's National Quantum Mission, the NQM, is huge. 6,000 crore, that's roughly $720 million US dollars, budgeted from 2023 to 2031. It supports the whole spectrum. QKD, computing, sensing, material science.
A major commitment.
Absolutely. And you also see partnerships forming, like with QNO Labs, startup in Bangalore. They're working on commercial QKD and QRNGs, even collaborating with ISRO, the space agency, and BEL, Fard Electronics Limited. That's crucial for turning research into real products.
So let's bring it back. What does all this mean for you, the listener? Why should you care about quantum keys and entanglement?
The impact could be quite broad. Think about defense. Truly secure communication on the battlefield, or back to HQ. Vital intelligence protected.
Okay.
Banking. Imagine fundamentally preventing data leaks in online transactions. Your financial details, much safer.
That would be nice.
Telecom. Layering quantum encryption over the fiber networks we already use. Boosting security significantly without a total overhaul. Space. Future satellites beaming down unhackable keys, maybe enabling that global quantum network.
And for science and tech itself.
It fuels innovation across so many fields. Quantum optics, cryptography, material science, precision engineering. It pushes everything forward.
It really feels like this DRDO IIT Delhi work, backed by the national mission, is putting India firmly on the global quantum map. That 1 kilometer wireless entanglement-based QKD, using fully indigenous systems. That really is historic.
It absolutely is. It marks a significant step towards building that quantum-secure digital future.
We've covered a lot today, tracing India's quantum journey, looking at the tech, the challenges, the potential. It really highlights that hack-proof future they're aiming for.
It does, and it leaves you wondering, doesn't it? If quantum communication does become widespread, truly ubiquitous, how might our daily lives really change? From how we bank to our personal privacy online, what new possibilities, but also maybe what new challenges might pop up in a world secured by quantum rules.
That's a fascinating thought to leave things on. We definitely encourage you, our listeners, to keep exploring this incredible field of quantum technologies. There's always more to learn in the deep dive.